Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
The next talk is Physics Education, Hideo Nitta.
Okay. Good afternoon. I would like to talk about the physics education and especially the quantitative analysis in the physics education research. And I must say that my English is very poor, and I beg your tolerance and patience for my broken English. First, I would like to talk about what is physics education research, and then quantitative and evaluation of the effectiveness of lectures, and then I would like to move on to the mathematical theory of peer instruction. Peer instruction is one of the active learning methods. And then I would like to discuss outstanding program of gender gap. And finally, I would like to mention a few challenges in physics education research. And physics education research is categorized into the discipline-based education research, which is recently established. And DBER is based on the research in education, psychology, and cognitive science with discipline-proper issues, materials, matters. And DBER is mainly developed in the field of STEM education, such as physics, chemistry, biology, and so on. But if you are interested you can find details about DBER in that book, which you can get webpage or National Academic Press. I mean, that free electronic copy of that book. In that book, the goals of DBER are given in this way, And if we change these general terms to physics, I can explain the goals of physics education research. The first, understand how people learn the concept, practices, and ways of thinking of physics. Number two, understand the nature and the development of expertise in the physics. And third, help identify and measure appropriate learning objectives and instructional approaches that advance students toward those objectives. And fourth, contribute to the knowledge base in a way that can guide the translation of PER findings to classroom practice, and identify approaches to make physics education broad and inclusive. And also, consideration part of physics education has a long history, but physics education research with that kind of goals has started more recently, around 1980s. And the most important finding is that by the traditional lectures, for many students, learning becomes just rote memorization. This is because students have very robust, naive conceptions based on their daily experiences. For example, we teach that according to the Newton's law, things without exerting force can move with constant speed. But students think things stop. Of course, this is based on the daily observation. You can see that things stop. To overcome such a strong naive conception, students need to change their way of thinking. They need conceptual change. That's not easy to occur. Therefore, we need interactive lectures. So, this picture shows the traditional lectures. This is one-way teaching. Of course, there is some Q&A, but the interaction between teacher and the students are not strong. In contrast, interactive lectures have not only strong interaction between professor and the student, but also interaction among the student. In analogy with physics, we may say that interactive lecture excites collective mode. In that sense, traditional lecture just excites individual mode. Of course, a few students, excellent students like all of you, may be excited by such a lecture, but most of others don't. But of course, it is natural that one may ask that interactive lecture really more effective than the traditional lectures? To answer this question, we need a quantitative method to evaluate the effectiveness of lectures. For that purpose, standard tests have been developed in physics education research. The most famous one is the First Concept Inventory, or FCI. FCI is a research-based multiple choice assessment instrument designed to test student conceptual understanding of Newtonian mechanics. It is composed of 30 questions, and the most important point is that incorrect answers or distractors are based on research. They're composed of a typical naive concept. And this is an example of FCI questions. Bowling ball accidentally falls out of the cargo bay of an airplane. As observed by a person standing on the ground, which path would the bowling ball most closely follow after leaving the airplane? Of course, correct answer is number 4, and other 1, 2, 3, 5 seems ridiculous. But my students answer like this. This is a typical result for university student. Only 30% of students answer correctly, and nearly 20% of students answered number 1. This is also a typical naive misconception student has. So by using such a test like FCI as a pretest, then after a set of lectures, we pose the same test as post-test. Then so taking the difference with post-test, average value of post-test, and that's a pretest, we can get a gain from the lecture. But that value cannot be used for a comparison of lectures, because simple gain depends on the absolute value of the pretest. To overcome this difficulty, Hayek introduced the normalized learning gain. Idea is very simple. The simple gain, he divides the most probable, the largest possible gain. That means 100 minus pretest average. So then we have the normalized value, which is in between 0 to 1. By using the normalized learning gain, it becomes possible to compare the effectiveness of various lectures in various universities and even high school. By using his normalized learning gain, he surveyed 62 courses that involves more than 6,500 students. And the result is this graph. The white bars, the G's of traditional lectures, and the black bars for interactive lectures. And you can see that the difference of traditional lecture, the average value 0.23 and the interactive lecture 0.48 is twice. So he concluded that the interactive lecture is more effective, twice as more effective than the normal traditional lectures. So this research triggers the reform lectures, because traditional lectures are ineffective. So now we have a variety of research-based interactive lectures, but I don't have time to discuss them, so you can, I recommend to, if you are interested in, I recommend to look the Joe Reddish's book, which you can find the PDF copy in his website. Here I would like to talk about the peer instruction a little bit. And because peer instruction is the simplest way that can reform traditional lecture to the interactive one. So the idea is to divide the traditional lecture into small mini lectures, maybe several 10 minutes lectures. And after such a small lecture, the professor poses the question like this, which includes most important concept in that lecture. So I'm sorry, this is in Japanese. And a car is moving with a constant speed. Which force that's acting on the car is larger? The forward force or the backward force? 1, forward force is larger than backward force. 2, forward force is equal to backward force. 3, 4. And students send individual answers by using the audio response system, a clicker. And the information is immediately gathered, and we can show like this. Here you can see that number 1 is more popular than the correct answer. Now, after this individual answer, students start the discussion. After the peer discussion, students send reversed answers. And you can find there is an improvement from 43% to 76%. So without teacher, student can learn by the peer discussion. This is a plot that gathers many results of peer instruction. The horizontal line is horizontal axis shows the fraction of a correct answer before discussion, and the vertical one is after discussion. For example, sorry. Okay, you can see that there's an improvement in general. Of course, some plot is that one is becomes worse, but in general, there is an improvement. And it seems there is some kind of regular behavior in these, with these plots. Right-hand side of the graph is taken from Mazur's book. So behavior is similar. So to understand the mechanism of peer instruction, I introduced the master equation, where N sub AQC is the number of students answering correctly after discussion, and it is given by the incoming process and outgoing process. The incoming process is where N sub B is the number of students who answer D, incorrect answer, before discussion, and after discussion, they change this incorrect answer D to correct answer C. So the transition rate is given by T sub CD, and the outgoing process is a similar discussion, similar consideration we can understand. And of course, this, I would like to emphasize that this equation is exact, but phenomenological. I mean that we cannot extract any practical consideration. So we need simplification, further simplification for this equation. Perhaps I don't have enough time to explain the details, so I just mentioned that we neglect the outgoing term and assume that the transition rate can be described in the power series of N sub B, and taking the lowest order. Then finally, we have a surprisingly simple equation with no free parameter. So this slide shows the comparison of theory with class data. But though that class data has a large dispersion, so maybe this agreement is more or less accidental, but to check this point, we introduced the peer instruction efficiency. We introduced this peer instruction efficiency in analogy with Higgs normalized gain. So this is a graph of the peer instruction efficiency in comparison with the class data. So agreement seems good. And by using this peer instruction efficiency, we can check what kind of concept test or critical questions are effective in peer instruction. And also identify a student difficulty in understanding the concept. But I have to skip, and I would like to go to the very important point about the gender gap. This is a result of Marson, the meta-analysis of FCI and other tests for various universities. Okay, 6 parts. There was absolute value of these score of, percent correct on the pre-test is different in different universities, but there is a consistent difference between male student and female student score. And by defining gender gap as the average value of percent correct for male student minus percent correct for female student, Melson obtained the value about 13%. And after reading this paper, I am interested in this, and I checked Japanese data and found same, very similar amount of value, about more than 10%. So I think this gender gap is international. And also, I tried to analyze the peer instruction data, and the peer instruction data also shows some gender difference on the gender gap. Of course, it depends on the question by question. So this is what I showed you before, shows the largest gender gap. You can see that male student answered correctly before discussion about 60%, but female student answered correctly only 20%. And even after the discussion, female student answered correctly a little bit more than half. So this means that female student has a stronger naive conception about this. Okay, so I will stop. So I skip this. And this is the overall result. And the correct answer before discussion shows that about 10% of gender gap. This is consistent with FCI result. But after discussion, the gender gap is reduced or eliminated. So it suggests that peer instruction or maybe any other kind of interactive lectures may effective for reducing the gender gap. But we need further investigation about this. So finally, I just mentioned about the few challenges. First one is the international comparison of quantitative data. Actually, physics education research is very local. So I mean that researchers in each country write their papers in their national language. I also, therefore, to access such a paper is rather difficult. So maybe I think that our Commission C4 team can do something about it. And second one is the greatest problem. Eliminating the gender gap is very important. So, but we have to overcome this problem in the future. And the final one is more theories for quantitative approaches needed for further research of physics education. Okay, that's all. Thank you very much for your patience.
Questions?
Thank you for the talk. I noticed in your previous slide that the high school students, the girls tend to do better than the boys, whereas that's not the case at the university level. The previous one, just, yes. No, this one. Is that true? Do you look into that? At a high school level?
Yes. TGU is Tokyo Gakugei University, and the high school is HS means high school.
Right. So did you look into why there's a reversal of trend?
Excuse me.
There's a reverse in the trend.
Reverse?
No?
No, just this is the coincidence about the years, right?
No,
reverse,
I mean...
What the reverse? I'm sorry, my English, I'm also...
if you look at the high school,
yes.
the female is higher, no, on this side. Your average PIE.
Right side,
yes.
This one. This is the peer instruction efficiency.
Right. So there's a reverse in the trend between high school students and university. No?
I don't think so. This is a kind of fluctuation.
Okay. The other thing I was wondering is whether you have been looking at this movement on flipped classroom. So in which case you, so what is flipped classroom is that you have no more lectures that delivered online, and then the students interact. So it's basically the same as your interactive lecture, yes, except no lectures is given.
You mean that
because nowadays we have technological advances, so people tend to make full use of
reciprocal lecture, you mean?
So there's no more lectures. The students view the lectures online, and then they go to a classroom and they do that discussion.
Yes, that's
Did you look into that?
Yes, that's also a kind of interactive method of lectures, but it varies. I mean, it's how the professor facilitates the lecture is very important, and it varies.
Bill?
So I have two questions. The first one is there evidence that the same kinds of conclusions about the ineffectiveness of traditional lectures would be equally true for graduate instruction, where presumably you've already pre-selected people who have a general appreciation of what physics is all about? Well, so that's the first question.
Yes, this is a very good question. Actually, I'm talking about introductory courses that include a variety of students. Physics major student is usually very motivated and becomes a learner, ideal learners. So they don't need to such encouraging for active learning. They can do the active learning by themselves.
So
no
what
problem.
you're saying is it's not so much that physics students get more information from lectures, it's just they learn in spite of the fact that we lecture to them badly.
But at least my experience and others also, sometimes, for example, quantum mechanics has a difficulty for students to understand. In that, really, they need conceptual change. So in that case, active learning works very well.
Yeah, well, I'm guessing that a lot of people have the same experience that I did, which was I learned physics by doing the problems. And I wouldn't have been able to do the problems if I hadn't gone to the lecture. But if all I did was ask whether I'd learned anything from the lecture, I probably would have, the answer probably would have been no. But then after I'd done the problems, I'd learned something, but I don't think I could have done the problems if I hadn't heard the lecture. So is that kind of dynamic captured by the, this kind of research?
Sorry, I would catch you.
Okay. The experience of myself and many of my colleagues is that we say we learned physics by doing the problem sets, not by reading the book or by going to the lecture. On the other hand, if I hadn't gone to the lecture, I wouldn't have been able to start to do the problem set. So what I'm wondering is that interaction between the learning that takes place by doing the problems, often in peer groups, is that connection between lecture and the kind of learning that happens in problems, in problem set solving, is that interaction captured by any of the research that's been done about physics education?
You mean this group problem solving in groups?
Yeah, what I'm saying is that if I just measured whether I'd learned anything by listening to the lecture, I might have found that I hadn't learned anything. But then, after I do the problem set, then I did learn something. But if I hadn't gone to the lecture, I wouldn't have been able to start to do the problem set. So, and I'm just wondering whether that idea has any validity, and whether any of the research that's been done has examined that kind of interaction between the different stages of learning.
Yes, I agree with you.
You had another question?
I did have another question, and if no one else is interested, I'll ask mine. So the second one is, what about it has to do with this peer instruction learning. And what I'm wondering is, when people change their minds because they've interacted with their peers, is it something where simply for that particular question, they've been convinced by the people who have thought more clearly? Or have they really learned something? In other words, if you ask them a week later whether someone jumping out of an airplane and opening the parachute and falling at a constant velocity, whether the upward force is bigger or smaller than the downward force, will they get that right a week later? A problem that is essentially identical but seems different to a naive. Did they really learn anything, or were they just convinced for the moment by their peers?
It's also good, very good question. That's a very important point. And I have to say that only one question doesn't work very work as induce the complete conceptual change. It is impossible. But it becomes a trigger to think about such a situation. So that's very important. 0 is 0, but 0.1 is quite different. So sometimes it works very well, but sometimes it works very slowly, but very important step.
Okay, thank you very much again.